So let us talk about spatial filtering. This spatial filtering, use of spatial mask of filtering is called spatial filtering. So we have earlier talked about this spatial mask or masks or window, or you can say a template, kernel. All these things, they have the same meaning, and they may be linear or non-linear. So what is linear and what is non-linear? Let us start with some linear filters. First of all, there is low pass filter. That means it attenuates or it eliminates high frequency components such as characterized by the edges and sharp details in an image. So low pass is actually allowing or passing the low frequencies. Low pass, just allowing the low frequency to pass. So net effect is image blurring. While in high pass, as the name suggests, high pass means only allowing the high frequency to pass. So attenuating or eliminating low frequency components such as slowly varying characteristics. Slowly varying characteristics are usually low frequency, and sharp edges and sharp details and edges are all high frequency. So this high pass filter, the net effect is actually sharpening of edges and other details. Then we have band pass. This is also a linear filter, band pass. It attenuate or eliminate a given frequency range. So, this is low frequency specific, this is high frequency specific. But this band pass is only, available for or work for a frequency range. And this is usually or used primarily for image restoration. Are of little interest for this image enhancement, which low pass and high pass does. These are the spatial filters. Let us take the examples. This is the low pass, this is the high pass, and this is the band pass. So filters in the frequency domain and corresponding spatial filters are like this. And basic approach is to sum product between the mask coefficients and pixel values. What we have learned, that there is a mask. Take each pixel value, take each mask value and multiply it, and all that kernel means if it is 3 by 3 kernel, take 9 values. If it is 5 by 5 kernel, take 25 values, add them and divide by the number 9 or 25. This is how these are the weights W1 to W9. So if the center of the mask is at this XY, then the pixel value at XY is replaced by any R. So this continues until all the pixels in the images are covered. For pixels which is near the boundary of the image, R may be computed using say partial neighborhoods or by padding the input appropriately. Because once the image is there, once you roll out this say kernel, then the last line, or you say last pixels or boundary pixels will not be covered, because we cannot apply this spatial mask there, because we don't have anything here, so we cannot apply. We can just apply one row or column minus. Okay, just beyond this we cannot go. Beyond this we cannot go. So one row and one column, the boundary row and column will always remain. So here we are suggesting that you can do some partial neighborhood, or what you can do, you can just transfer this value to this final value, this value to this value, or say padding, add any value 0 or 1 here. So usual practice is to create a new image with the values of R. This is the final image after applying the kernel. So order-statistic nonlinear spatial filters, that means we have nonlinear spatial filters also operate on neighborhoods. These are nonlinear spatial filters. Their operation is based directly on pixels in the neighborhood under consideration. They do not explicitly use coefficient value as in linear spatial filters. So example of nonlinear spatial filters are, first of all, median filter, max filter, or min filter. Median filter, as the name is suggesting, that it will compute the median. So it computes the median gray level value of the neighborhood. This is used for noise detection. And maximum filter, it computes it finds the brightest point in the image. or a filter, you can say. So from k from 1 to 9, this is zk. That means this is talking about a mask or a kernel. So this kernel takes all the brightness values, compute the maximum or find out the maximum and replace the center one by the maximum. And this one it computes for a kernel. Let me give the example. What median will do, it will take from W1 to W9, or not, this W1 W9 will not be taken, only Z1 Z2 Z9 means the actual pixel value. So computation of this Z1 to Z9 is the pixel value. A median of these 9 values will be computed and will be replaced inside it. And for the min or max, the minimum value of from Z1 to Z9 means the pixel values from Z1 to Z9 will be computed and that will be replaced here. Again, we'll filter, the same stuff will be done. So we have smoothing filter. The shape of the impulse response needed to implement a low pass filter indicate the filter should have all positive coefficient. If you have a low pass or smoothing filter, all coefficients will be positive. And for a 3x3 mask, the simplest arrangement is to have all the coefficients value equal to 1, like this. This is neighborhood averaging. So if you want smoothing, this can be done, and all you can place 1. So the response, would be the sum of all gray values of for the 9 pixels in the mask, and divided by 9. That will be the average only. So this is averaging, neighborhood averaging. So this could cause the value of R to be out of valid gray level range. This solution is to scale the result by dividing by 9. So this is, I'll tell you what I was trying to suggest that time. This is averaging filter example. First of all, you take this is an image of 528 by 485 pixels of some Hubble Space Telescope. Now this is image filter with a 15 by 15 averaging mask, right? And this is the result of thresholding. So once you average them, it will become blurry. But once you put some threshold, you see these points or these values are so very much visually perceiving. This is the smoothing filter example. This is the original image, 500 by 500 pixels, and from this to this, all this 5. This is the result of smoothing with square averaging filter. The mask is here 3, 5, 9, 15 and 35. So the black square is the top of the size 3. These black squares, these are the black squares. These black squares at the top of the size 3, 5, 9, 15, these 25, 35, 45 and 55 pixels respectively. Their borders are 25 pixels apart. The borders are 25 pixels apart. Now the letters at the bottom range is from 10 to 24 points in increment of 2 points. And the larger letter at the top is this 60 points. This A is 60 point. The vertical bars are 5 pixels wide. These vertical bars are 5 pixel wide and 100 pixels high. These are 100 pixels high. And the separation is around 20 pixels. So the diameter of the circle is 25 pixels. The diameter of these circles are 25 pixels and their borders are 15 pixels apart. Their intensity level ranges from 0% to 100% and black in increments of 20%. These are final black, this is white. The background of the image is 10% black and the noisy rectangles are of 50 into this noisy rectangle. These rectangles are 50 into 120 pixels. So what smoothing filter does, this is an image and once you apply a 3x3 kernel, this will become like this. 5 by 5 kernel pixel, the image will be like this. 9 like this, 15 by 15 like this, and 35 by 30 like this. So this is how you have to find out which kernel you should use, what exactly do you want, and what result is suitable for your purpose or application. So one problem with the low pass filter is it blurs edges and other sharp details. You see that these are the blurring effects, especially on the edges. So if the intent is to achieve noise reduction, one approach can be to use median filtering. If you want to do just noise reduction, you can use median filtering. The value of each pixel is replaced by the median pixel value of the neighborhood as opposed to the average. You don't have to put the average. You can just compute the median. So what is happening here, that if I find out an average, so sometimes what happens, that if some pixel is very high, this pixel, what its actual value was, it will become very high. Averaging will give this problem, but median will not give this problem. That is why it is saying that if you want to just remove noise, median is the good solution. And particularly it is effective when the noise consists of strong spike like components and edge sharpness, which is to be preserved, right? And the median m of set of values is such that half of the values are greater than m and half of the values are less than m. So to implement, sort the pixel value in the neighborhood, choose the median and assign this value in the pixel of interest. And it forces pixel with distinct intensity to be more like their neighbors. So what median does is, you arrange your brightness values of that particular area, neighborhood, in ascending or descending form, and take the center one. So that will not give you a higher value, because average can give it. This is the median filtering example, and you are going to appreciate this for sure. This is a X-ray image of circuit board corrupted by salt and pepper noise. And this salt and pepper noise, if you want to get rid of noise, you can use either averaging mask, or you can use a median mask or median filter. So this is the result achieved by applying 3x3 averaging mask, and this is the noise reduction with 3x3 median filter. Now, which one is good? Of course, this is the best. That is why I am suggesting that you must use median filter if you want to remove this salt and pepper noise. These are the sharpening filters. The shape of the impulse response needed to implement a high pass filter, which indicates the filter should have positive coefficient near its center and negative coefficient in the outer periphery. So for a 3x3 marks, the simple arrangement is to have the center coefficient positive and all other negative. You might be recalling that in smoothing we took all as 1, but here for sharpening we need to highlight some point, okay, and we need to you can say suppress the boundary points. That is only way by which you can find out the sharpness or the edges. For that, the boundary values are given -1 number, and the center one is highlighted, or it is given a higher value, higher weight. So this is 8. So this is how your sharpening filters are designed, and this is one of the sharpening filters. So you must note that the sum of the coefficient is 0. This is very important. You have to use a value so that the addition is 0. So when the mask is over a constant or slowly varying region, the output is 0 or very small. That is why we took it as if you combine them, it will be 0. So this filter remains this 0 frequency term. So eliminating this term reduces the average gray level value in the image to 0, and result will be somewhat edge enhanced image over a dark background. So reducing the average gray level value to 0, this implies some negative gray levels. So the output should be scaled back into the appropriate range, like in our 8-bit image 1 to 256 or 0 to 255 for a 256 gray level color map MATLAB image. This is the example of high pass filter example, which was formed when we applied this filter. This is a high pass filter. Now we have this high pass filter. It may also be computed by high pass can be computed by just take the original and subtract it from low pass. So multiplying the original by an amplification factor yields a high boost or a high frequency emphasis filter. So high boost will be original minus low pass. This is A is some multiplication factor. So if A is greater than 1, part of the original image is added to the high pass result. This is partially restoring low frequency components. and the result look more like original image with a relative degree of edge enhancement that depends on the value of A. This is a constant. So it may be implemented with the center coefficient value W is equal to 9A minus 1. So A, multiply A by original image by some A, and you see that we can just add and delete this origin because we have taken A minus 1, and this original minus low pass, you know what is this? This is high pass. So high boost can be attained if we multiply this original by A minus 1 and we add the high pass. So this is high boost filter. If we take A as 1.1, if we take A as 1.1.5 and A 1.1.2. So this is how you can also get a great sharpening filters with some degree of variation, that is A. Now we have derivative functions as well. The basic first order derivative of 1D function fx is the difference, you know it. df by dx is fx plus 1 minus fx. This is the basic first order derivative of 1D function. And the second order derivative is fx plus 1 plus fx minus 1 minus 2fx. This is the second order derivative, which is the difference. So derivative functions is, first of all, this is the illustration of the first and second derivative of a 1D signal, right? 1D, first and second derivative of a 1D digital function representing a section of horizontal intensity profile for an image. So this one and this one, data points are joined by dashed lines, see, as a visualization aid. So this is on the left hand side we have this as intensity, and this is the scan line. This is the first derivative, you see the values, and this is the second derivative, right? So you can see the first derivative is this, and the second derivative is this, see, right? These white boxes represent the second derivative, black boxes represent the first derivative. So these derivative filters, differentiation may be used for edge enhancement, that means detail sharpening. So the most common method of differentiating is the gradient. For fxy, the gradient of f at xy, this is the image, our original image, which is defined as, we can define the gradient as df by dx divided by this as a matrix, df by dx here, and the second one is df by dy. So magnitude will be the magnitude of this del f, that's it, delta f, del f by del x square plus del f by del y square, and this is under root 1 by half. Okay. So the derivative filters, this is z1 to z9, these are the actual pixels. So magnitude of the gradient at z5 can be approximated in a number of ways. The simplest way is to use the difference z5 minus z8, these two, in the x direction, and z5 minus z6 in the y direction, because in image, you know, this is what? This is the y direction and this is the x direction. So just compute it, z5 minus z6 and z5 minus z8, and just compute it, square it, add it and take under root. This can be approximated as z5 minus z8, this is modulus, plus z5 minus z6 modulus. So the caused cross difference may also be computed to approximate the magnitude of the gradient, that is z5 minus z9, right? And z6 minus this z8. This can be known as a cross difference, just for approximation. So this can be implemented by taking the absolute value of the response of the following two masks and summing the result. This is called the Roberts cross gradient operator. So what we are doing is the absolute value of the response of the following two masks. These are the Robert cross gradient operators and summing the results. So this is the extension of 3x3 mask. The yield what? This is the final value, and the difference between first and third row approximate the derivative in the x direction. The difference in the first and third columns first and third rows and first and third columns. See, these are the values only in rows. These are the values only in columns. So the first and third column approximate the derivative of the y direction. The pivot operator masks may be used to implement the above approximation. Now this was the robot. This was the pivot. Also, we have a Sobol operator. This mask. This may also be used to implement the derivative approximation. Right. Again, this is the two values in rows and two values only the column values have some number, but you can very well find out if you add it what you are going to get. You are going to get the zero value. So the Sobol operator are widely used for edge detection, right? And all the mask coefficient for all derivative filters sums to 0. This is 0, indicating 0 response in a constant area, as expected for a derivative operator. So after application of this derivative filter, generally the output will be scaled, as in low pass and high pass cases. So the result is then thresholded by setting any values above the threshold to white, that is 256 in MATLAB we use with the 256 gray value color map, and all below the threshold are set to black, that is 1 in MATLAB, or left with their initial values in fxy. So the derivative filters may be applied only in x direction, only in y direction, and in both direction, taking either the sum or maximum of the responses from the filter mask. So this is a derivative filter example. This is the original image, and we have applied Sobol filter image here. If you go to this MATLAB, you can just use derivative filter, and you can use Sobol and various numbers here. This is the derivative filter example of Sobol filtered image and Sobol filtered image for different values. See, horizontally, this is horizontally giving you the edges, and this is vertically giving you the edges. This is the other examples also, giving max values. So thank you so much. I hope you got a bit idea about these filters. We are going to go into the detail shortly.